Hello everyone, I'm Dr. Kang. So today we're going to look at the Neyman-Pearson Lemma and its proof. So the Neyman-Pearson Lemma is a useful result in theoretical statistics, a result which we can use to construct a best critical region of a certain size, where the size corresponds to the probability of type 1 error. And this best critical region is best for testing a simple null hypothesis against another simple alternative hypothesis. All right, so to begin, we just go through the lemma. So the lemma says the following. So let x1, x2 until xn be a random sample of size n from a distribution with probability density function fx theta, right? So theta is the parameter of the model. So the joint PDF of x1, x2 until xn is just the product of the PDFs, right? It is denoted by L of theta. So if you have a discrete random variable, so your PDF just simply changes to the PMF, right? The probability mass function, okay? Suppose we test H0, which is a simple null hypothesis, against another simple alternative, right? Theta is equal to another value, theta 1. Now for some positive constant k, right? So let C be a subset of the sample space, okay? Such that the chance of getting a point in C under the null hypothesis is equal to alpha, right? Which basically is saying that your C is your critical region, right? And alpha is your level of significance. 2, the ratio of the likelihood function under the null against the alternative is bounded by k for each point in the critical region, right? And number 3, the ratio of the likelihood functions under the null hypothesis against the alternative is greater than or equals to k for each point in the complement of C, right, outside of the critical region. If the hypotheses are true, then C is a best critical region of size alpha for testing H0 against H1. All right. So essentially, this is what the Neyman-Pearson lemma says. Now, in order to continue with the proof, let us be clear about what is meant by a best critical region, right? So we all know something about the critical region, which is basically the subset of the sample space where if we get some value in this subset, then we would reject the null hypothesis, right? So that's the critical region. So we need to define what is meant by a best critical region, right? In what sense, right, it is said to be a best critical region? Because there could be at the same time several possible critical regions that are of the same size alpha, right? So we need to be clear about what is meant by best. Okay, so now we're going to talk about the best critical region, right? So, so the best critical region is defined as follows, right? So let's see, denote a subset of the sample space. Okay. C is called a best critical region underline, of size alpha for testing the simple null hypothesis against the simple alternative hypothesis if for every subset A of the sample space, so this A is another subset of the sample space, right, for which the probability of getting a point in this subset under the null hypothesis is also alpha, okay? So it has the same size as C. Number one. Okay, so number two, the probability that we reject, so this is the rejection region, yeah, we reject the null hypothesis under the alternative is greater than or equals to the probability of rejecting the null hypothesis under the critical region A. All right. So basically, we can have two different critical regions, A and C, right? And both of them have the same size alpha, okay? And we will say that C is the best critical region if both A and C, they have the same size, but then the power, so this is actually the power, right? So the probability of rejecting the null hypothesis under the alternative. So this is the power of the test for C, right? For the critical region C, and this part is the power of the test for the critical region A. All right. So the power of the test when the critical region is C is greater than or equals to any other subset of the same size. If that happens, then we will say that the C is the best critical region, right? In the sense that its power is the largest among all other possible critical regions, right? So you have, maybe you have like other subsets of A, B, D or whatever, right? They all have the same, although they all have the same probability of rejecting, committing the type 1 error, alpha, but then the power to reject the null hypothesis under C is the largest, right? In that sense, we say that C is the best critical region, right? To illustrate this, it may be useful to look at some sketches. So suppose this is the distribution of the test statistic, right, under the null hypothesis, okay? So let's say, suppose this is our critical region, right? So of size alpha, so the area under the curve here is alpha, right? Now, if the alternative is true, then the distribution of the test statistic would be something else, like say something like this, okay? So if this is our critical region, so we will reject H naught, right, when we get values, right, in the critical region, right, which is this part. So this would be the power to reject H naught, right? Okay, I'm assuming H1 is true, right? When H1 is true, we look at this distribution of the test statistic. All right, and so here this part is the power. Now, in the same manner, we could think of a different. Let's suppose this would be our C, right? We could actually define some A some region A that's made up of these two pieces, right? So this we would define it as the region A. Okay, this part a union this section, right? So this is under the null, the distribution under the null. So let's look at the distribution under the alternative, the specific alternative. So over here, the power would be made up of this part plus this part, right? So this plus this would give us the power to reject H naught, right? Assuming H1 is true. But this is for the critical, so this is for the critical region A, and this is for the critical region C. So if C is the best critical region, that means the power here is greater than or equals to the power here, right? So obviously it would be very tedious to consider all possible subsets of the sample space, right, where we want to do this comparison, okay? So it'd be very, very tedious if we try to figure out all these combinations. There might be infinitely many, so you can't really check all of them, right? You can't really consider this area under the curve and then compare against all possible subsets. So this is where the Neyman-Pearson lemma comes in handy, right? It's a theoretical result that guarantees that you will if you follow a certain procedure, right? Then the critical region that you construct will be the best critical region, right? So the procedure is that we just simply need to find solve for this inequality, right? So for each x1 until xn in C, right? So basically we simply need to consider the two likelihood ratio of the two likelihood functions, one under the null, one under the alternative, right? So if the alternative is more likely, right, so the likelihood in the denominator will be much larger than the likelihood in the numerator, right? So when it is sufficiently large, then this k here will be small, right? So as long as we can find some k such that this ratio is sufficiently small. Now this k is dependent on your alpha, okay? It's dependent on the level of significance, right, which is the probability of committing type 1 error, okay? So this k is dependent on alpha. So we just need to find, so the critical region can be found by solving for this inequality, all right? So that's the and once you get the inequality under when you solve for this inequality concerning the ratio of likelihood functions, then under the Pearson lemma, Neyman-Pearson lemma, then you will have a best critical region, right? So operationally, it becomes very easy to do, right, to find the best critical region, right? Okay, so now, so once we know this, then we need to understand why, right? So let's look at the proof. So the proof of the Neyman-Pearson lemma. Okay. So, right, essentially what we want to do is that if C is the best critical region, then the power to reject the null hypothesis, right, would be greater than or equals to the power to reject the null hypothesis, okay, under the alternative, but with a different critical region, right? So A is the critical region of size alpha, okay? So this is what we need to show, all right? And we need to show this by using the hypothesis in the Neyman-Pearson lemma, okay? So essentially, if we are concerned with continuous random variables, right? So the left-hand side here would be basically the integral, the multiple integral over the region C for the joint density function, right? So okay, so this is dx1, dx2. So this is a multiple integral, okay? And so essentially this is what we want to show, right? Okay, under the alternative. So we have this, right? So technically we want to show this result, okay? If you have a discrete random variable, then you simply replace the multiple integral with the multiple summation, right? And the probability density function is replaced by the probability mass function. Okay. Now, so to make this easy to write notationally, so this is equivalent to, I will write this as just using one integral notation. And this part here is the likelihood function, right, under the alternative. And basically, so for the second part, I will write it like this, okay? All right, so essentially, this is what we want to prove. All right. Okay, so to continue, so first we take note of the following, right? So first we can recognize that our critical region C can be written as C intersect A union C intersect A complement, right? Okay, so these two sets are mutually exclusive, so they are disjoint, okay? And A can be written as A intersect C and union A intersect C complement, right? But that note that the order of intersection is irrelevant here. So C intersect A is actually the same as A intersect C. So because of this, we can write the integral can be broken up into two parts, right? Okay, plus C intersect A complement. And similarly, we have this A intersect C plus this, right? Okay. So then if we take the difference, right, the difference between these two integrals will be, so here you can cancel, so you basically have the difference between these two integrals, but the region of integration is different, okay? All right. Now, so let me clear some space here. So we'll keep this result, right, for reference. Okay. Now, if you recall the hypothesis number 2, right? So by hypothesis number 2 in the Neyman-Pearson Lemma, right? So we have L, the ratio has to be bounded by K, right, for each point in C, right? Okay, so here this inequality implies that L of the likelihood function under the null is under the alternative, right? It's greater than or equals to 1 over K of the likelihood function under the null hypothesis, right? Okay, so this is basically just rearrangement, right, from this hypothesis. Now, if this is true for each point in C, it implies that it is true for each point in C intersect A prime, right? Because C intersect A prime is a subset of C, right? Okay. So therefore, I'll take integral C intersect A prime L of this will be equal to, so you basically integrate both sides, right, with respect to the region C intersect A prime, A complement, okay, L theta naught, right? Okay, so we have this result. And then we have by hypothesis number 3, so let's clear some space here. By hypothesis number 3, what do we have for hypothesis number 3? So hypothesis number 3, so we would have the converse, right? Okay, is greater than or equals to K for each point in C complement, right? So if that is the case, then it would be also true for each point in A intersect C complement, because A intersect C complement is a subset of C complement, right? So then from here we would have L of theta 1 is bounded by 1 over KL of theta naught, right? So if you rearrange, you can see this very clearly. So here we take integration on both sides, right? So we will get integral with respect to this region, A and C complement will be bounded by 1 over K intersect A intersect C complement L theta naught, right? Okay. But then, so here we want to work with the negative of this integral. So we will multiply both sides with negative. So we'll have negative here, we have negative here, and therefore the inequality sign will reverse. Okay. So now we have these two results, these two inequalities, right? Okay. We simply add, so these two inequalities, we can simply add both of them, right? We add 1 plus 2, right? So the left-hand side, if you add them together, you get this part. And the right-hand side, if you add them together, they become the following. They become 1 over K integral C intersect A prime L theta naught minus integral A intersect C prime L theta naught, right? And this will be greater than or equals to, right? So to continue here, okay? All right. So this part here is an important result, okay? So we end up with this inequality, okay? So we are about done here. So the final step is to do the following. So let me clear some space here and keep the results on the same page so that we can follow the argument more closely. Okay. Right, now from here, so we're going to look at the integral, right? Just forget about the constant here, okay? So we're going to look at the integral, the difference between the two integrals. So we can write it as follows: C intersect A prime. We can add C intersect A and then cancel the term that we introduce. Okay, so this is a useful method in proofs, right? You basically add zero, you add something and then you cancel it back, right? The idea is the following. So when you do this, then we can actually rearrange the term, right? So that's the whole idea. Okay, so you add something, you cancel back, but then you don't cancel it, you use it, you use the term that you introduce to group with other terms so that you can combine them and get a new result, right? So here this part will be A intersect C prime L theta naught, right? Okay, so basically now you have this thing and essentially this part you can write it like this, right? So what do you have here though? So the left hand side here will be C, right? The region will be C because this region is complement to this region, right? And similarly on the right hand side is the same thing. Okay, so this part is the other part's complement, so you basically have A, right? Okay, but then once you get this, then we are in business, because by definition this part here is equal to alpha, right? Because this is basically just the probability of rejecting the null hypothesis, right? When the null hypothesis is true, right? Because you are integrating with respect to the region C, right? The critical region. And here is also the same, right? This region is A, and both of them have same size alpha. So alpha minus alpha equal to 0. Okay, so then this is 0, so which means that so this part here is 0, right? So then you finally prove this result. Okay, you finally prove that the power, right, to reject the null hypothesis under the alternative for region C is greater than or equal to the power to reject the null hypothesis under the alternative for region A. Okay. Right, so this concludes the proof, right? I hope it's been clear enough. Okay. Okay, thank you for watching.